Hi folks, so we're going to talk today about flexography plates. So you think about it, if we're going to print something, we've got to be able to transfer whatever our graphics are, our art, and we need to take that and put it onto a, a device essentially that will transfer that art onto the substrate on the printing press. So this area right here is in my personal opinion, is a very interesting area of flexography. It's an area where technology has grown the most in the last 20 years. It's really where all the quality of the print really comes from. If you have really good plates, you can have a really nice looking finished product. And if you don't have good plates, well, things don't come out that good. So let's talk about this for just a little bit. So sometimes, in the world of graphics and printing, we call a plate, kind of like an umbrella term for the plate, it's called an image carrier. Now we call it the image carrier because it's what carries the graphics in the process and transfers it. So it's a medium that holds the inked image and transfers it to the substrate. And like I said, it's most commonly referred to as a printing plate, but sometimes it's not necessarily a plate. It could be a variety of things. Now in Flexo, it is called a plate, but in the world of printing itself, there's a variety of different forms of image carriers. So when it comes to flexography, we deal with what's called a relief image carrier. Now what that essentially is, and when I say a relief, it's a raised surface. The image is raised out of the base of that plate material. This material is compressible, and that's one of the advantages of flexography, is that it has a little give to it, so that when it transfers, it's transferring in a way, and when it comes in contact with our substrate or whatever we're printing on, it has a little bit of give to it, and that's a big advantage. And because it conforms to the substrates, so if there's any irregularity to the surface of it, it can kind of get down into those irregularities. Think about cardboard, for example. When you print on cardboard, it kind of has a little bit of a wavy surface to it. Well, the flexography plate can conform to that wavy surface, and that's a big advantage to why a lot of things are printed this way. It also kind of compensates for if there's an irregularity or an imperfection in how the plate comes in contact with the substrate, so it's forgiving, and that's important. And then also, if there's any mechanical imperfections, like for example, maybe gears that start getting worn down a little bit, if there's a little give, a little play, this compressible surface allows it to help minimize the impact of some of those shortcomings that the machinery might have from age and use and that sort, and abuse, because that does happen as well. So that's one of the biggest advantages, is that it will kind of help minimize those imperfections, and it allows us to print on a wider range of materials. So there's different types of image carriers for flexography. We got plates, and plates are flat, and that's what we'll use in our lab. And then there's also cylindrical, and these are plates that are already in a cylindrical form, because our plates are going to go on, the flat plates are going to be wrapped around a cylinder, but the cylindrical ones are really neat because they're already in a tube shape, and that in itself is helpful. But the downside to these cylindrical ones, or sometimes they're referred to as sleeves, actually they're more commonly referred to as sleeves, I'm trying to use the the most let's say academic terms possible, but people call them sleeves. And the nice thing about, whenever we're using a cylindrical one is that it can create a nice continuous pattern. That pattern goes all the way around. There's no start and stop to it. And that's really good for solid backgrounds or any instance where maybe you might be, when you do this, you can kind of use different size cylinders. And by doing that, it can, you can have a small continuous pattern where maybe you have a larger one that puts information on, and that can save time and energy. But by far the most commonly used plates, or image carriers in Flexo are going to be the flat sheet material. It's a lot less expensive, and you also don't need quite as robust technology in order to create these plates. So let's kind of talk about just the parts of an image carrier, or let's just start calling them plates. That's what everybody says. Everybody says plates. The technical word is image carrier, but everybody says plates. So I'm gonna start saying plates. So what I have here is, let's just say an enlarged view of the side of a finished plate material. As you can kind of see, there is a raised area here that's coming off of the base of this plate. So let's kind of talk about the different parts. So and these parts are in no particular order really. So you have the plate floor. Now what the plate floor is, it serves a very important function. It's what anchors the image to the plate. It's what anchors that raised image off, and it also provides stability for the plate material. So it's a very important factor, and when we make the plates, we can determine where this kind of shelf or where the base of the plate starts and stops, and by controlling that, we can provide more or maybe even less stability for the image that is on top of it. Next, we'll talk about the image area. So this is the raised area. This is the area that's going to come in contact with the ink and then transfer the ink to the substrate. It's the actual printing surface. So you can think about the image area as, well, that's the image. That's where the image is that's raised out of that plate floor. Next, we have the caliper. So the caliper is the overall thickness of the plate. Now in flexography, there's a wide range of thicknesses of plates that you can choose from. And each one of these has a different kind of use. And a lot of times it has to do with what type of material that you're printing onto. Sometimes you might need a big thick plate, that's about 1/4 of an inch thick. And think of this, that the thicker it is, the more compressible it is. So if you're printing on, say, again, let's talk about corrugated or cardboard. With cardboard having that wavy pattern, you need a thicker, more compressible a plate so that it can get down into the recesses of that fluted structure. They call that waviness a fluted structure. So the thicker it is, the more compressible it is, and it can get down into those areas. So it can be anywhere from 32 1/1000th of an inch to 25 1/100th of an inch or 1/4 of an inch. So the plates in our lab we use are 67 1/1000th of an inch. A lot of times whenever you're referring to plate caliper, one term that we use is one's called mils. And a mil is 1/1000th of an inch. So in our lab, we use plates that are 67 1/1000th of an inch. But a much easier way of saying that is that we're using plates that are 67 mils. So it's just another way of communicating plate thickness is through mils, and it's just a whole lot easier to say mils than 1/1000th of an inch. So a great little term to have in your back pocket just to ease communication. So think of it this way: the thicker the plate, the more squeeze it has; the thinner the plate, the harder that it would be. Next is going to be the relief height. So that's how high is it from that base, the plate floor, to the tip of the printing surface. So that height, this height can be varied, just like the plate floor can be varied, depending on the needs of the job. So we're not going to get too much into that right now, but just know that by controlling our process, we have a direct impact in the quality that we get out of our plates. Next, we'll talk about the shoulder. Okay, so the shoulder is the side of that raised image. Now notice here that it's curved, and there's a reason for that curvature. If you think about this, when you look at a bridge, it doesn't have just straight up and down supports throughout it. Most of the time, the supports are curved, and by having that curve, it distributes the load better, and it makes it a more stable structure. So the same thing, the same concepts of physics are being applied on a much smaller area of our plate. So by having that curved shoulder, it allows the image area to have more stability. So it's not wiggling around, it's more taut, and that's what we want. It'll still compress, but it won't wiggle, and we don't want it to wiggle. It'd be like putting a paintbrush onto our substrate. We want a nice kind of stable area that will compress, not collapse. Okay, so that's the purpose of the shoulder. We have the plate backing. So when we look at the plate, on the back side of it, it's going to have a very, very thin polyester layer right there. And it's pretty thin, but it's really important because the material that the plate is made out of is compressible, which means essentially it stretches. It can move around, but we need something that's stable that eliminates the stress on the back side of the plate, so that when we do wrap it around a cylinder, it doesn't stretch or distort in any kind of way. So we don't really have to do a whole lot for it. It's already built into the plate material when we purchase it or get it from our distributor, and but it serves a very important purpose. All right, so the type of material that our plates are made out of it's called photopolymer. Now what photopolymer means is essentially it's like a light sensitive plastic. You can kind of think of it that way. It's a plastic that reacts to light. So when light hits it, it hardens. And that's kind of the process that we're going to go through to make those plates. We're going to use a series of light exposures to transfer that image down into the photopolymer. So there's a variety of different types of photopolymer that you can get. There can be a liquid form, like literally, you kind of form and make the plates, like literally make the raw plate kind of from scratch, and that's very commonly used when you need something that's very custom, but those types of situations are becoming more and more limited because of, again, that technology. Like I said, like this technology has grown for quite a bit in the last decade or so, and some of those options are just not as necessary as they used to be. Precast sheets, which is just like we were talking about before, they're just flat raw materials, and all they really are is just that polyester backing and then a layer of photopolymer. We'll talk more about kind of the raw plate material in just a minute. And then it also can come in the cylindrical form or the sleeve form that I mentioned earlier. So let's kind of dig into like what a raw photopolymer sheet looks like. So again, this is kind of a zoomed in version, so we can kind of get a better view of it. So the first thing that you're going to encounter with this raw material is just a polyester cover sheet. All that cover sheet is just polyester. It's thin, remarkably thin, and it is simply just there to protect the material through shipment and handling. So whenever we go to make our plates, it's something that just gets pulled off and discarded. It actually can be recycled. So in a lot of instances, it very much so is. But really, all it does is serve the function to protect it from handling and transport, so that the photopolymer, which is the very expensive part of the plate, does not get damaged. Now, the next layer is called the laser ablation mask. Most people call it just the mask, or maybe a carbon mask. And what this is a very delicate, extremely thin, very opaque black layer that is on top of the photopolymer. So what happens in this particular layer is that whenever we need to transfer our art from the computer stage of things onto the plate, it doesn't like etch down into the photopolymer. What it does is we use a laser just to literally vaporize that carbon, and what it does is it creates essentially like a negative on top of the plate whenever we go through the laser. So what happens is we bring up our image on the computer and we send it to the laser, and the laser will just go and it etches or ablates. Ablates is the technical word. That carbon mask layer, and it removes what is essentially just the image or the graphics that's going onto the plate. So this layer, like I said, is very, very delicate. So anytime that you pull away that protective sheet, whenever it's pulled away, you need to be very careful with handling it, not to accidentally scratch like a ring on your finger, or your fingernail could very easily scratch this very delicate layer. Next is the money layer. It's the photopolymer layer. So it's what takes up a vast majority of that caliper that we're talking about. I mean, in our lab, like I said, our plate caliper is 67 mils. The photopolymer layer of that overall caliper, it makes up, out of 67 mils, it probably makes up about 64 and a half of that thickness. So it's what takes up the most, and it's that's really, when we buy plate material, that's where the money really goes, is in that layer, because this stuff is not cheap to make, and also it has to be very, very precise and very it needs to meet a bunch of specifications so that it can ensure the quality of our final product. And then the very last thing is that that polyester backing sheet that I already mentioned earlier. So when we talk about the stages of photopolymer plate making, there's essentially 5 major stages or steps to it. So, and we're going to kind of look at each one of these stages individually. So here is a large plate. It's being put into an exposure unit. And it has the back side of the plate up. So like what we're seeing right here, that's the back side of the plate, and the exposure unit is going to close down, and what's going to happen is that we're going to expose the back side of the plate. Now, the reason for the back side of the plate exposure is so that that's what sets the floor height of the plate. So this particular exposure is really one of the most important because it really defines the floor height, the height of the floor, but it also determines the relief height or the height of that raised image that's coming off of it. So it's very important. It's the stage that needs to be monitored the most. And what happens is, and really this particular exposure doesn't take very long. It's about in our lab, I believe the calculation for it right now is 1 minute and 50 seconds. So it's just an overall wash of light on the back side of the plate. Got to start there. Next, we're going to image it. So once we've done the back exposure, we're going to remove that protective sheet like Andy right here is doing. And we're then going to take that plate and load it into our laser. So this large gray machine right here, Andy's about to open it up. And he's going to load it in. Now inside of this device, there is a laser that is going to take our image and our graphics and transfer it on into that laser ablation mask or the carbon mask. So the heat from that laser is going to strike it. The carbon is essentially going to vaporize, and that vaporized carbon is going to be sucked out of the machine and collected. And then whenever this process is done, we're going to have all of our graphics etched in or ablated into the that carbon mask layer. So at this point, we're going to take it out of the laser. And these videos were taken at Flint Group, which is a very large plate manufacturer. They have a technical location here in Charlotte. Andy Knapp right here is a graduate of our program. He's been working with them now, I believe, for like 7 or 8 years. He does very good for himself. He makes extremely good money, and he is really a recognized individual in the industry. So he has taken part in many large research projects and has contributed in a lot of ways to this industry as a whole. So, and he loves his job. So anyway, getting back to the main exposure, as you can see, that parts of that mask have been removed. He is going to move it back to the exact same exposure unit that did the back exposure. And he's just moving it over there. And what's going to happen is now the light is going to shine through that laser ablation mask. And the areas that have been ablated, the light's going to pass through and it's going to harden. All the areas that are still black are not going to get exposed, and that material is going to stay soft. For lack of a better word, it's not going to harden. This process takes a little bit longer. In our lab, I believe the current calculation is an 8-minute exposure right here. But isn't that an amazing machine? It looks like something out of Star Trek, I tell you. So now what we'll be using in our lab is essentially the exact same as what they're using. It's just on a slightly smaller scale. Our machines do the exact same thing. They're just smaller because we don't need gigantic plates like that. All right, so once it comes out of the main exposure here, what's going to happen is now all the material that has not hardened needs to be removed. So there are a variety of different ways to remove that material. He's going to go put it into this processing unit that is behind him. This is called a solvent processor. Now what it does is he's going to move it into the machine right here. It's going to pull it in, as you can see it here. And as it moves through the machine, it's going to be soaked down into a solvent. That solvent is going to kind of, let's just say, loosen up the material a little bit. Then it's going to go through a series of brushes that's going to literally scrub the unexposed material away from the plate. So that's solvent based, and that's very commonly used. But there are other ways to do it. You can do the same thing without using a solvent. You can just use water, and the water, will soften up the unexposed material. And then again, just brushes will brush it away. Another way, and the more common way that the industry is going these days, is it's called a thermal processor, and that's what we have in our labs, a thermal processor. The way it works is a little bit different. It uses heat to essentially gel the unexposed material, and then it comes in contact with an absorbent material that wicks away or just absorbs that gelled material, and it goes through that process about 10 times, and it's a little bit of a faster process. It's a little bit of a cleaner process, but the quality is not quite as good as the solvent-based one that we're seeing here. It's faster, it's easier, but the quality is a little bit smaller. But that quality is getting better and better, and that's why people are making more of that move to the thermal processor like we have. Now, because he used the solvent-based processing, it has to go through a drying stage. The plate material absorbs some of that solvent, and now it needs to dry it away. As you can see now, when he pulls it out, all of that carbon mask and everything is gone. It's all been processed away or just washed away. You can even see in this image here that we can already see that raised area, which is really where it's really starting to look like a plate now. So he's just going to put it in there, and with solvent-based plates, the drying time can vary considerably. It can take, in some processes, as much as an hour to do. But like what we do in our lab, since it's a thermal process, it's based on heat and there's no liquid component to it, it comes out the end of the processor dry. So we don't have to do the stage. So again, that's also another reason why the thermal process is a little better, because it's much faster and we can skip this drying stage. Now, the very last part, because right now we have something that pretty much looks like a plate, it functions like a plate, but we're going to put it through 2 exposures. One is called a post-exposure, and what the post-exposure does is that it makes sure that all of the photopolymer in the plate has been exposed. Because right now there might be little pockets that maybe didn't get exposure, like in between the relief and the floor. There might be this little tiny area that isn't hardened. So the post-exposure is just one last wash of light to make sure that everything is exposed. The final step is called light finishing. And what light finishing does is it hits it with a different spectrum of light. It hits it with what's called UVC light. And what this does is it kind of changes the molecules on the surface of the plate, and it makes it much less tacky. It makes it less sticky, for lack of a better word. And this makes the plate transfer ink better. It also prevents it from picking away little fibers from the substrate as it rotates over and over again. You don't want your plate to be sticky. You want it to be you don't want it to stick and pull fibers off. So that's what this final stage of it does. So the entire process of plate making, like in our lab, from the time we sit down at the computer and image with the back exposure and everything and all that put together, we can do it in less than an hour. But it's a whole lot of just hurry up and waiting, you know. It's not a stressful process. So we have a lot of students that really enjoy going into this area. For one, it pays pretty good. You know, it's a good area to be in. Also, you get to work with some really interesting technology. You get to work with technology that is changing and growing on a rapid basis. But also, you are able to work in a nice, clean environment. You know, you don't really have to get your hands dirty if you're working with plates. So it pays well, high technology, and very clean process. And also, you know, climate control is very necessary when using this technology. So you're always in a nice, cool room, no matter what. So, so that's the basic overview of the plate making process. So once we make the plate, we need to make sure that it is, you know, within standard. Because like I said earlier, we can manipulate how the plate forms based on our exposure. So after the plate comes out, we need to inspect it. You know, we need to take a look at it, make sure that we're not seeing any issues. Like, you know, for example, we want to make sure that there's no like surprise marking on there, which could happen. We could have accidentally scratched it in the process, you know, during the imaging, or maybe our exposures might be a little bit off. So, but the first thing you want to do is just visually inspect it. Does anything look weird? So that would be step one. Next, we want to do some measurements on the plate. So these measurements is like what we want to do is we want to measure the plate floor. Okay, how high is that plate floor? We want it to be within a particular range. Now, what that particular range is going to be determining on, you know, what, you know, you currently do. Like in our lab, we want the plate floor to be between 45 and 49 mils. So we need to be within that window. And if we're not within that window, that's a very good indicator that one of our exposures need to be adjusted. It could be caused by, you know, the bulbs in our machine getting older and not putting out as much output. It's very possible. It's very possible that maybe one of the bulbs has burned out. These things happen. You know, light bulbs, you know, they don't last forever. So we need to monitor it and just make sure and ensure that our plate is within the specifications that we need to be able to, you know, produce the quality and the consistency of what we're doing. You know, another option, especially if you have very fine elements in it, like what we call halftone dots. We haven't really gotten into what halftone dots are in this course yet. But what I want you to understand is that there are these analyzers that will go and it will inspect, you know, how perfect those dots are, if they're in the right pattern, if they're reproducing correctly, and also if there's any areas where those dots just aren't forming for some reason or another. Now, with this particular step of it, you know, we don't have one of these analyzers here at the school, but we do regularly take plates and we'll send them off to Flint Group, and they'll analyze it for us and give some feedback on how to improve our process. So once we have a finished plate, we've got to take it and we've got to transfer it and apply it to a cylinder, because all of our flat plates need to be wrapped around a cylinder whenever they're going through the printing process. So we use a double-sided tape, which was called mounting tape. It's very commonly referred to as sticky back, but sticky back is it's a proprietary term that's used by one of the mounting tape manufacturers. So it's not really the most it's not the most accurate term to use, but it's kind of like, you know, like a thermos or Kleenex. It's a brand name, but it is commonly used for all brands. So if you hear sticky back, what they're talking about is mounting tape. So like I said, it's a double-sided tape. It adheres the plate to the print cylinder, and it has a very big impact on print quality. So actually, let me back up for just a second here. Oh wait, no, we're going to get to that. Okay, so the mounting tape has a big impact on how sharp things are how sharp of a print we're getting. So one term is called solid ink density, and solid ink density is basically a solid area of print. So depending on what mounting tape we choose, we can make those solids print lighter or darker. Like I mentioned earlier, halftone dots. Sometimes those dots, maybe we don't want them to compress quite as much. If they compress too much, those dots get bigger and they grow. So we call that dot gain whenever those dots grow larger than they're supposed to. So you can control dot gain with our mounting tape. When we look at these dots that have been printed, you notice how there's this dark kind of circle around the outside of them, and what that is that's essentially those dots being compressed too much, and because they're compressed too much, they grow larger than they're supposed to. And also, what mounting tape can improve is slur and banding. And you can kind of think of like slur. Slur is kind of like smearing. We don't want the ink to smear, obviously. We want it to print cleanly. So, but there are instances where if we don't make some good choices when it comes to our variables related to the plate, it can encourage slurring or smearing. And banding is another term where just essentially, the print might be slightly lighter or darker in different areas, and the choices that we make with our mounting tape can impact that. So essentially what you need to know about mounting tapes is that they can be softer or they can be harder. And the softer they are, the more compressible they are. And the harder they are, the less compressible they are. So this graphic, I think, really illustrates what's happening very well. So if we have a very hard mounting tape, what's going to happen is that the mounting tape itself is not going to compress very much. What is going to compress is the plate material. Now, the advantage to this is that it's going to give us a very dark, solid area. So if our goal is to have really dark, deep, rich, solid prints, then a hard mounting tape is going to be a good choice. If we have a lot of very fine detail, like halftone dots, in this instance, we don't want the plate to compress that much. We want our mounting tape to compress, and that makes those dots print a whole lot more clean. But what you'll notice, though, is that the solid areas, they don't print as deep and dark and rich. So the choices that you make whenever, just from mounting the plate can directly impact how clean or the outcomes of the print. I mean, what happens is, let's say we have multiple colors that we're printing. The colors that maybe are the background that has a large area of solids. Well, we might use a harder mounting tape, but maybe there's some fine detail like very small type, very thin lines, or halftone dots like a photographic image or a gradient of some sort. On that color, we might want to go with a softer mounting tape so that those areas are better represented. So there are some issues that we can have with mounting tapes and plates, and like, for example, air bubbles. I mean, like, little air bubbles can pop up underneath our plate, in between the mounting tape and the plate, or it could even be between the mounting tape and the plate cylinder. So these are something you want to be aware of and take notice of whenever you're mounting your plates. Try to avoid the air bubbles. A lot of mounting tapes these days have what are called micro channels in them, and they're little like crisscrossing areas. And what they're designed to do is allow these little air bubbles to escape once it has been applied to the cylinder. Okay, so most all the mounting tapes that we have in our lab are going to have micro channels, and what we just do to avoid these air bubbles is use it's like a roller. It's actually called a brayer, and we just roll it on top of the plate once it's done, and it pushes those air bubbles out. But the problem is that if we don't do that, anywhere that there's an air bubble, that plate is going to be lifted more than it should in that area. And since it's lifted more in that area, there's going to be more compression than in that area than in the rest of the plate. So those areas are going to be darker, So you definitely want to avoid any kind of air bubbles. Another issue is whenever you wrap it around the cylinder, and a lot of times when we print, the plate literally can lift up off of the cylinder. And I'm kind of exaggerating here, but maybe it's just a little bit. But the best way to avoid that is just to take some isopropyl alcohol, like I'm doing right here, and I'm going to clean the back of the plate, and I'm also going to clean the print cylinder. What this does is it goes and it removes any kind of oils or solvents that maybe have gotten picked up on those surfaces, either from your hands or from a cleanup earlier. And this just helps it adhere better. It's a small step of just cleaning that will make life a whole lot easier once we're trying to print our plates. So the thing is just kind of remember with this is consistency is key. This entire process is particular. It needs to be it needs to be done in a very regimented way. So the first thing you want to do is optimize your equipment, make sure that it's functioning the way that it should be. We're going to monitor it so that we're going to do it. We're going to inspect it after it's done. We're going to do our measurements. We're going to document what we're supposed to document. And then we're going to do it the exact same way every time. And if you do that, you're going to have very good quality plates when you're done. Also, it's going to make you more marketable. You're going to, if you're making plates and you're passing those plates off to, press person, their job's going to be easier, and that's really what our goal should always be, to put together the best possible product of in anything that we're doing. So these 3 steps: optimize, monitoring, and repeating, and doing everything the same way every time, is always going to make the entire process better. So that's my quick crash course into what plates are, how they're made, and also the mounting tape as well. Because we really when we're trying to understand these variables, the variable of the plate and the variable of the mounting tape are very closely intertwined. And I'll just go ahead and say that I never really realized how much of an impact that mounting tape plays in quality until I had been working in this industry for a very long time. And so, but what I learned is that it's not, you don't just use one tape for everything. If you think about what you're doing, you can produce something that, and if you understand these variables, you can put together something that's far superior. And really that should always be our goal. This is also what is going to set you apart from other people in this industry. It's how well you really understand all of these concepts that go into the flexographic process. All right, so that brings us to the end of things. Thank you very much for paying attention, and talk to you next time.